Okay, hello everyone. Welcome to our seminar. Today we are very happy to have Professor Akira Ohnishi from Kyoto University to give us a talk. Let me first introduce to you about this seminar. Let me first make the introduction in Chinese, then I will make it again in English. 各位老师同学，欢迎大家来到复旦核物理前沿开放论坛的第38讲。
Recording in progress.
那我是复旦大学物理系和现代物理研究所的黄旭光，今天很荣幸来主持复旦核物理前沿开放论坛的第38讲。这个系列讲座是由复旦大学核科学与技术系、现代物理研究所、核物理与离子束应用教育部重点实验室主办，由 Nuclear Science and Techniques 和核技术刊物协办。那报告通过 Zoom 会议平台进行直播，大家在报告结束后可以通过平台上进行提问。同时呢，这个系列报告也得到了口想科学平台的直播。那么今天呢，我们很荣幸的邀请到日本京都大学的这个 Akira Ohnishi 教授来给我们做报告。那么在这个报告之前呢，让我来介绍一下我们的 speaker。Professor Akira Ohnishi is currently a professor at the Yukawa Institute for Theoretical Physics at Kyoto University, Japan. He got his PhD at Kyoto University in 1992 after working at Osaka University and Hokkaido University. He took the current professorship since 2008. His research interests are very broad, including the lattice QCD, the nuclear equation state, and the phase diagram of QCD matter, and also the fuel body interactions in the hadronic matter, and so on. He has published more than 230 articles, and he is currently the editor of the PTAP, and he also serves in a number of physical societies, including the Physical Society of Japan, the Nuclear Theory Group Committee, and the APCDP Committee. So today he will tell us the challenge to the hyperon puzzle. Okay, so Akira, okay, please.
Okay, thank you very much for a nice introduction. And I'm Akira Ohnishi from Yukawa Institute, Kyoto University. And this work is in collaboration with Asanosuke Jinno, one of my students, and Koichi Murase in Yukawa Institute, and Yasushi Nara from Akita International University. Okay, and in this talk, I'd like to talk about the challenge to the hyperon puzzle and the lambda potential density dependence at high densities. And this talk is composed of 5 parts. First, I'd like to introduce some hyperon puzzle of neutron stars. And next, I explain the lambda potential from chiral effective field theory. And next, we apply this lambda potential from chiral EFT to the first heavy ion collisions and lambda binding energy in hypernuclear. I choose this subject because I understood that the Fudan University is a physics department and nuclear physics forum members are interested both in the nuclear structure or the mean field or density functionals, as well as heavy ion collisions like Shugan and Wanzong. Wanzong is a member of Fudan, I'm not sure. But therefore, the combination of heavy ion collisions and the hypernuclear spectroscopy may help us to understand the hyperon puzzle of neutron stars. That is the subject of this talk. Okay. And the first part is already published in Physical Review C last year. And the other one is in preparation. Therefore, I'm afraid that the second part is you can do the similar work by yours in a month or so. But since this is still in preparation, please submit your articles 1 month later or something like that. Please, okay. Okay, I think, I put the PDF, wait a minute. Okay. I put the PDF of my slide to the chat. Therefore, if you want to take it, then please see that PDF file. Okay, I believe that one of the grand challenges in nuclear matter physics is the equation state and the QCD phase diagram. And the current problem of, for example, the equation state consists of the symmetry energy, that is the difference of energy per particles or in pure neutron matter and symmetric nuclear matter. And the difference between this energy is called symmetry energy. And of course, the symmetric nuclear matter equation state is relatively well known, especially around the saturation density. But for the pure neutron matter equation state is not known, at least experimentally. But there are a lot of ab initio calculations, such as the variational calculation and the variational calculation and the green function multicolor or something like that. And the various nuclear experiments gives you the constraint on the saturation parameters, symmetry energy parameters around the saturation density. But at higher density or the error bar, uncertainty becomes much larger. And this part determines, for example, the neutron star size. This is one of the big problem in nuclear matter physics. And the next one is in nuclear matter physics problem is the hyperon puzzle. And for example, the empirical hyperon potentials cannot sustain two solar mass neutron stars. And in 2010, then most of the hyperonic matter equation state are ruled out because of the observation of the two solar mass neutron stars. And this is one of the largest problem. And the third problem maybe is a QC phase transition at high densities. If there is a first order phase transition boundary in high densities, then it should be connected with the color superconductor. And it may be possible to probe the color superconductor in a laboratory heavy ion collision experiment. Then it's great. And when we have a larger asymmetry, isospin anisotropy, then the phase boundary, first order phase boundary should shrink. And in neutron stars, then we may have the crossover phase transition or the first order phase transition. And is there any first order phase transition in neutron stars, or can we observe some hints of the first order phase transition from heavy ion collisions in BMNI scan or CBM or at FAIR or the NICA or JPARC High, which is just planned, or HIAF is a kind of future project in many countries, including the LIGO-Virgo-Kagra gravitational wave detectors. And neutron star is a kind of a good, unique laboratory of dense matter physics. For example, the outer part of neutron stars is made of the nuclei, neutron-rich nuclei, and dripped neutrons and electrons. And the position of the neutron drip or the mass or the spin anisotropy of this nuclei is closely related to symmetry energy. And the outer core of neutron star is made of asymmetric nuclear matter of neutrons and protons, and which is whose charge is cancelled by electrons and muons. And the inner core is a kind of very good playground of quark hadron physics. We expect QCD phase transition or the hyperon admixture or meson condensation or something like that. And therefore, this is a kind of a most unknown dense matter in the universe. And we'd like to distinguish this the phase of this inner core, and we can, in principle, we can distinguish these candidates from the mass radius curve precisely, then we can guess the equation of state. And in addition to that, we may have the cooling rate or neutron star oscillation to guess the equation state of dense matter, but the most direct one is the mass radius curve. Why? Mass radius curve and the equation states are connected by the so-called Tolman-Oppenheimer-Volkoff equation, which is nothing but the general relativity version, a general relativity version of the static matter star. And when we have a strong gravitational force, which balances with the pressure difference of the outer part and lower part. By considering the balance of the gravitational force plus the outer pressure with the inner pressure, then we have the non-relativistic version of the TOV equation is obtained like this. By modifying this epsilon to the enthalpy density and this mass inside the radius of R is replaced by the M plus P something, pressure something. And in the denominator, we have the redshift factor, redshifter factor square in the denominator. This is the TOV equation. And the mass inside radius R is given like this. And but with these equations, we have three unknown factors, pressure variables, pressure, energy density, and mass. But we have just two equations. Then one more equation is necessary, and that is nothing but the equation of state. Pressure as a function of energy density. Then if we give the equation of state, then by solving the TOV equation from the center, starting from mass equals 0 and R equals 0, and integrate out up to some surface where the pressure becomes 0. Then the equation, when the equation of state is given, then we can calculate the mass and the radius at the same time. And for a stiff equation of state, the mass becomes larger for the central density as a function of central density, and can sustain a larger neutron star mass. When the equation of state becomes softer, then the maximum mass becomes smaller and the radius becomes relatively smaller. Therefore, if the astrophysicists observe the mass and radius very precisely, then we can constrain this MR curve. Then we can go back to and judge the equation of state. Therefore, this relation is known to be 1-to-1 correspondence. Therefore, if we observe this curve very precisely, then we can determine the equation of state of neutron star matter. And from here, then it becomes work by theorists, but from the equation of state, we can guess the composition of the neutron star matter. And people believe that the hyperon should appear at 2 to rho 0 saturation density. And but then the maximum mass of neutron star was predicted to be 1.3 to 1.6 solar mass before 2010. But in 2010, then the 2 solar mass neutron star is observed, and the 1.3 or 1.6 solar mass maximum mass is not enough to explain this one. Of course, before that, the 1.67 solar mass neutron star was observed, but many of massive neutron stars' lifetime is 3 to 6 months. I mean that is some people say that they have found very massive neutron stars or very compact neutron stars, but there are a lot of mistakes in such kind of observation, and people did not believe that 1.67 solar mass neutron star it really exists. But after the observation of 2 solar mass neutron stars via the Shapiro delay, which is really the general relativity effect, then people now believe that the 2 solar mass or 2.08 solar mass neutron star should exist. It means that the hyperonic matter equation state or the chaotic matter, chaon condensation equation state are ruled out. But these curves are based on hypernuclear physics, and starting from the two-body lambda n interaction or something like that, something is wrong. And there are several proposed solutions, such as the three-body lambda n repulsion gives repulsive lambda potential at high density. Then the hyperon cannot appear in neutron star matter, and the equation state is unchanged even if we include the hyperons in the theory. And we can solve the hyperon puzzle. This is one of the solutions. And the other solution is the transition to quark matter before lambda appears. Before lambda appears around here, then some quark matter component is mixed and stiffens the equation state. Then we may the hyperon puzzle may be solved. If nuclear physics fail to explain the hyperon puzzle based on experiments, and the astrophysicists may say that it is because of the modified gravity, and I mean that the general relativity need to be modified. That is a very interesting direction to study, but as one of the nuclear physicists, I'd like to pursue the first two possibilities, and I concentrate on the first possibility, the repulsive lambda potential at high density. Okay, and recently the repulsive lambda potential at high density is predicted or proposed in terms of the chiral effective field theory. And for example, the Gerstein, Kaiser, Weise, Munich group published a paper of chiral EFT, and they said that with the three-body repulsive term from mainly from the next to leading order, then it stiffens the lambda potential at high densities, and the single particle energy of lambda is always larger than the neutron chemical potential. Then the lambda does not appear in neutron stars. That is a possibility. Of course, the chiral FT is a first principle method, but not ab initio. I mean that they contain some parameters, tunable parameters. Therefore, it's not completely the prediction, but it is maybe reliable, possible way. But of course, the yet unknown parameters are tuned to support two solar mass neutron stars. Therefore, the repulsion at high densities needs to be verified. Such kind of density behavior need to be verified from hopefully with the nuclear physics experiments such as heavy ion collisions or the hypernuclear spectroscopy. And in addition to this density dependence, the momentum dependence is also necessary in this kind of chiral EFT, because chiral EFT is a theory based on the expansion in terms of the momentum. Then the lambda potential in nuclear matter necessarily have the density as well as the momentum dependence. And momentum dependence was calculated in a little different way, but in chiral EFT by Kono in 2018. And we'd like to examine this kind of momentum dependence as well. Okay, then how can we examine repulsive lambda potential at high densities? And one of the candidates observable is the direct flow from heavy ion collisions. When two nuclei collide with each other, and when the Lorentz factor is not too large, then we have hot and dense region around here in the participant region, and the incoming nucleons is kicked out to this side or this side. And the directed flow is defined as the cosine phi or the px, as a function of the rapidity. And therefore, this repulsion says that it is V1 is increasing function of the rapidity. That is the expectation. Okay. And this directed flow has been utilized to study the equation of state. And then how about the case of lambda? That is the case of this work. Another candidate is hypernuclear spectroscopy. And density-dependent lambda potential from chiral phi is different from empirical or standard potential. For example, we show the empirical lambda potential in nuclear matter from Ransko-Yamamoto-Hartree-Fock calculation, and that's density dependence looks like this. But in the case of the chiral EFT, then the density dependence is somewhat different, even below the saturation density. If we have different density behavior, density dependence as a function of the density and below the saturation density, then this difference should be observed and should be accessible from hypernuclear spectroscopy. Therefore, we'd like to examine the repulsive lambda potential in nuclear matter at high densities via the directed flow from heavy-ion collisions as well as from the hypernuclear spectroscopy. That is the thing which I'd like to discuss here. Okay, this is the introduction. And is there any question, comments up to here? Okay. Can I proceed? Okay, let me proceed. And the first part is lambda potential from chiral EFT. Okay, chiral EFT is a kind of first principles method which respects the chiral symmetry and other symmetries in QCD. And it is given as a perturbative expansion series as a function of momentum. And recently, the decoupled saturation model is proposed by these people, mainly from Munich. And the next to leading order chiral perturbation theory, the chiral effective field theory says that there are several terms which generates the three body force. But the interaction, for example, the vertex of this one or this one is not known. And in order to determine these new low energy constants, then we need more data. But the hypernuclear data is not very rich, and we cannot determine these low energy constants. Therefore, these people propose that the n next to leading order diagrams generating three body force are assumed to be saturated by decoupled baryon diagrams. For example, this diagram, this part may be replaced by the delta or lambda star or sigma star, not lambda star, okay, sigma star or n star or delta star. And this is also decoupled resonance. And by using these diagrams, and in nuclear matter, one of the baryon is is assumed to be has a loop, and these three body force is replaced by the density dependent force. And they made some kind of Bruckner-Hartree-Fock calculation and obtained the lambda potential in nuclear matter. And by tuning the one parameter, then they found that there are several parameters where the there's no hyperon appearing in neutron star matter. That is their recent result. And not very recent, 2020 result. And therefore, we use this chiral lambda potential and in heavy ion collisions as well as the hypernuclear spectroscopy. And therefore, we parameterize the lambda potential as a function of density and momentum as the power series of Fermi momentum rather than the density. Fermi momentum to the cube is the just proportional to density, and Fermi momentum to the force is proportional to the density to the forces, and the Fermi momentum to the fifth is proportional to the density to the 5/3. Okay, and the momentum dependent interaction is assumed to be proportional to k squared times the nucleon density for the use for the case of hypernuclei. And for heavy ion collisions, this density dependence is too strong. Therefore, we assume that the momentum dependent force is sum of several terms of Lorentzian type. Okay. Then we use the following 5 parameter sets. Chi3 means that the Gerstein Kaiser Wise density dependence with 3-body force, but without momentum dependence. But in the case of Chi3 mom, then we include the momentum dependence. Chi2 are the versions where the 3-body force is ignored. And for the nucleons, and we use the Scar-Leon 4 force for hypernuclear spectroscopy, and we use so-called that MS2 momentum-dependent soft interaction are used. And for comparison with these lambda potentials, Lansky-Yamamoto potential is assumed to be the empirical standard potential for lambda, and we use this interaction. Okay. And for specification, we show the result of the Gerstein-Kaiser-Wise potential band like this. Since the chiral FT contains some error bars, therefore we show this error bar. And we parameterize this the density dependence via the Fermi momentum expansion for without 3-body force or with 3-body force. Compared to these curves, then the Lansky-Yamamoto interaction has somewhat weaker density dependence at lower densities, but is a much more attractive potential for the at high densities. In the case of the MS2 for nuclear force, and people sometimes say that the lambda potential is proportional to the 2/3 of the nuclear potential, which shows like this, and which is similar to the Lansky-Yamamoto interaction, but there are several factors between these. Okay. For the momentum dependence, then for the Skarm-Hartree-Fock calculation we show later, in that case, the just k-square dependence is enough until around the Fermi momentum at normal density. Okay, and this is the Chi3 mom result. I mean that GKW with 3-body force and Kono's momentum dependence. And the Lansky-Yamamoto interaction case, it looks like this. Therefore, the momentum dependence is much weaker than the chiral EFT result. For higher energies, then the k-square dependence is too strong. For example, in the case of the nucleons, then we see this kind of momentum dependence is known to be good and fits the nucleus potential very well. We multiply 2/3 for the nucleon potential, but this kind of dependence is known to be good. But therefore, the k-square dependence is too strong at higher densities. Therefore, we use the kind of a Lorentzian sum like this. And there's a, for lower momentum, we can use the chiral FT result, but higher momentum, we do not know. Chiral FT is not very reliable at high density, therefore high momentum. Therefore, we compare the result of these differences at high momentum. Okay, these are the potential which we use in heavy ion collisions as well as hypernuclear spectroscopy. Okay. Questions, comments? Okay. Okay, let me proceed. Now, I'd like to compare the result of the chirality, the lambda potential from chirality with the real data. And I show the star data, therefore the Huanzong may make some kind of objections or comments. And high energy heavy ion collisions are interesting in the sense that at LHC and top RIC energy, then we should have the quark-gluon plasma. At these high energies, then the initial condition may be given by the color glass condensate. And just after the collision, we see a lot of color electromagnetic field in the direction of the collision axis, and which summarizes and make a QGP. And finally, it hadronizes and the hadrons are detected. But at the lower energies, such as the below the transition energy, for probably this one, maybe 10 JeV. Yes, New Shu said that this transition energy may be 8 JeV, but I'm not sure. If this is 10 JeV, then the incident energy is around 50 JeV per nucleon, which is very high. But at below this one, then we should have the very dense and hot hadronic matter. Oops. I'm sorry. Oh, I already cut. I'm sorry. The hot and dense nuclear matter is formed, and we can probe the equation of state of these hot and dense hadronic matter. Okay, and collective flow for heavy ion collisions is known to be, has been utilized to extract the equation of state at high density. And as I already explained, when we have the high pressure in the participant hot and dense participant regions, and incoming nucleons are kicked, and the V1 becomes increasing function of the rapidity, and we should have the slope of this one. Okay, and previously there are a lot of discussions about this slope. To be specific, people measured the px average as a function of rapidity, and its slope is named as the f flow value. And for example, the Daniel Ritz, Roy Lacey, and Bill Lynch published a paper in Science in 2002, and they say that the flow slope is explained by the soft equation of state, where the incompressibility is 167 or 210. And we have also published a paper in 2000. And in the case of the hadronic cascade, then we cannot explain the data. But when we use the mean field potentials in the relativistic mean field theory, then we can explain the data of flow slope parameter well in the region below AGS energy, I mean the 10 JeV per nucleon. But recently, okay, I'm sorry, before that, And for this analysis, we use the nuclear transport theories and combination of the mean field dynamics plus Boltzmann equation. And the combination of these are generally called the Boltzmann-Uhlenbeck equation or the Landau-Vlasov equation or some other names. But anyway, it looks like this. Okay, and this is velocity times nabla, and this shows the force acting on particles, and the right-hand side is the collision term. When two nucleons collide with each other and change the momentum to the F3, P3 or P4, then the nucleons are Pauli blocked with a probability of 1 over F. And this one is the inverse process where the momentum 3 and momentum 4 nucleon collide and gives the momentum of the interest, and is a P2. Oh, it is also Pauli blocked. And this is a collision term. And when potential, mean field potential is given to assumed to be 0, then this shows the just a Boltzmann equation, and sometimes it is called cascade. And it includes the two-body collisions. And when the right-hand side collision term is ignored, this one is considered is called the Vlasov equation. And the Vlasov equation is just a Wigner transformation of the time-dependent Hartree theory. Therefore, this properly includes the effect of the mean field at low energy. Therefore, this kind of transport equation connect low energy mean field dynamics and high energy collision dynamics of two-body collisions. And therefore, I think that the applicability of this transport theory is very large from up to before the QGP is formed. When QGP is formed, then the degrees of freedom becomes very different from nucleons. Therefore, we have to extend this kind of equations or use the fluid dynamics or hydrodynamics. And but before that, I think that we can apply this kind of transport equations. One of the versions of this transport equation is so-called the quantum molecular dynamics, as proposed by Rolf Ahiren in 1991. And this BUU equation can be solved. A Vlasov part of the equation can be simulated by solving classical equations for test particles whose distribution gives the phase space distribution function F. And usually for one nucleon, we put 110 or 100 test particles and try to describe this distribution function well. And solve the classical equation, classical canonical equation motion for these test particles. But by putting the test particle number to be 1 per nucleon, then it becomes just kind of the classical molecular dynamics simulation. And this is, you can consider that it is an approximate way to solve the BU equation, but the fluctuation strength is physical. Because in the case of the BU equation, and when we put a lot of test particles, then the fluctuation of this distribution function becomes very, very small. It becomes deterministic. There's no fluctuation. But therefore, the physical fluctuation need to be added later in addition to solving this BU equation. But when we put one test particle per nucleon, then it becomes, fluctuation becomes physical. This is a kind of barter trait of the how to say, the precision and the physics. And we use so-called relativist quantum molecular dynamics, which is a constraint Hamilton dynamics. And when we would like to describe the dynamics in a covariant way, then we need 8 n degrees of freedom, and n is the number of hadrons or nucleons. I mean, 8 means that's the time plus 3 xyz coordinates, and there's E plus energy and 3 vector momentum, px, py, pz. Then this 8 n degrees of freedom is necessary to describe the covariant dynamics. But the usual equation motion only contains 6 n variables. Therefore, we need 2 n constraints. And these constraints are given by the on-mass shell constraints plus time fixation that is discussed by Zorge, Stecker, and Greiner in 1989. And but their constraints are very, very complicated and cannot be achieved in a practical way in a calculation. Therefore, the RQMD/S simplified is proposed by Tomoyuki Maruyama in 1996. And by using the simplified time fixation method, then we can solve the constraint by analytically, and the equation motion becomes very, very simple like this. Okay. But the V is a so-called one particle potential, which is similar to the single particle potential, but that is a little different. But the problem is that we always have this kind of 1 over gamma factor, which becomes very small at high energy, high momentum. Therefore, by using this kind of the on-mass shell constraint, then this potential is essentially the Lorentz scalar, and its effect becomes weaker at high energy. Therefore, we have developed, not we, but Yasushi Nara developed the stronger potential effect via the vector type potential. When we use this kind of vector potential type, then the equation of motion in RQMD becomes somewhat different. And this V star factor is a kind of a ratio of the P star 0 and P mu. Therefore, this mu runs from 0 to 3, and the P0 over P0 is 1. Therefore, this factor remains large even at high energy. And therefore, with this kind of vector potential type, then the potential effect remains at the high momentum. And this was necessary for the discussion of proton directed flow. And in 2014, Starr gave very, very interesting data of the directed flow, starting from 7.7 JeV to 11.5 JeV up to 200 JeV. And the proton flow's slope shows non-monotonic behavior as a function of the colliding energy. And this was not understood for 8 years. None of fluid and hybrid model explains the beam energy dependence with a single US. Of course, one can explain each data point by changing the equation state as we did before. We changed the equation state from here to here. Then we can explain each data point with separated equation state, but with a single equation state, we could not, nobody could understand this kind of energy, colliding energy behavior. But a solution is found by Yasushi Nara and me in last year. by using this kind of the vector type potential and relativistic mean quantum molecular dynamics. And I did not explain the detail of the contents of this paper, but the slope parameter shows changes sign around 10 J, but we can explain this energy dependence by using the RQMD with the vector potential mode for protons. Then, what happens for lambda? Directed flow of lambda is measured also by the star collaboration in the beam scan program. And for protons, as I already explained, the change of the slope sign at around 10 J is explained by this framework. And by using the similar potential for lambda, then it roughly explains the slope parameter reasonably well, but not perfect with the momentum dependent soft version 2 times 2/3 for hyperons. Not bad, but not very precise. Therefore, we used the lambda potential from chiral FT. Okay, and the chi2 or chi3 are fitted to the Gerson-Kaiser-Weiser potential without or with 3-body force. And the result of the previous page is this MS2 times 2/3 for lambda. This is just this blue line, and which roughly explains the data, but the slope is not deviate from the data by 10-20%. When we use the lambda potential from chiral FT, then it really fits the data very well. Therefore, we can reproduce and explain the slope parameter for lambda with the chiral FT. Okay, but the moment when we use the momentum dependence as well, then we underestimate the slope parameter by 30% or something like that. When we use a softer momentum dependence, as we explained, this one, we use this is the chiral 3 mom with soft momentum dependence. Then we still underestimate the data, but just 10-20%. That is the situation. Therefore, probably also in the case of the proton, we slightly underestimate the slope, V1 slope at lower energies. Therefore, we may increase the slope a little also for lambda by some other things. Okay, let me summarize this part. The repulsive lambda potential chi3 enhances the V1 slope and gives results close to data when momentum dependence is ignored. But the momentum dependence of lambda, U lambda, reduces V1 and its slope, while the density dependence affects less. The mechanism is not known yet. Provided that the other effects, such as the more repulsive sigma potentials, we use the same potential of lambda and sigma from chiral FT. It's a kind of the approximation, or we do not know the sigma potential from chiral FT. Therefore, there is no other way. And stratified nuclear equation state with K incompressibility of 240 MeV rather than 210 MeV, then I think that the slope may be enhanced a little. then the chi-3 momentum with soft momentum dependence would be a reasonable solution, we hope. But is there any other way to constrain the density and momentum dependence of U lambda? Then we use the hypernuclear spectroscopy. Any question, comments? Okay.
Yes.
Yes.
I
Okay.
have a quick question. By the
Yes.
lambda directed flow, do you mean the net lambda or just the lambda?
Just lambda, not net
Okay,
lambda.
just the lambda, not including
Yes.
the anti-lambda contribution.
Right. And because the at 3 jab or 4.5 jab, where the slope is significant, then the production rate of lambda bar is not large, and we have to add a lot of error bar to the calculated result, and the calculation time becomes much longer to accumulate a lot of lambda bar to be created in transport model calculation. Therefore, we concentrated on just lambda.
Okay. I see. I see. Thank you.
Okay, let me go to the lambda binding energy in hypernuclei. And separation energy or the binding energy of lambda in hypernuclei is relatively well known from 80s or 90s. And its mass dependence is given like this, where the horizontal axis is the mass number of the core to the -2/3. And since this is the nuclear radius, 1/, nucleus radius squared, then it is proportional to the kinetic energy of lambda. Therefore, the straight line around the large mass region, since that it is, and it converges to the same value of the binding energy in nuclear matter limit, since that this is a contribution from the kinetic energy. And this mass dependence is well fitted by the, for example, the spherical Hartree-Fock calculation, Skarm-Hartree-Fock calculation. And one can, people believe that from this mass dependence, we well know the lambda potential density dependence well. And but the obtained lambda potential from hypernuclear spectroscopy causes the hyperon puzzle. Therefore, let me try to understand this binding energy from the lambda potential from chiral EFT. And there exists at least one work which uses the chiral EFT to the lambda binding energy by Heidenbauer and Vidania. And but this one just uses the next reading order NLO13 potential, which does not contain the three-body force effect. And with this result, then we cannot understand the mass dependence of the lambda binding energy well. Therefore, how about the case of the next reading order with decoupled model? And Skarm-Hartree-Fock for lambda hypernuclei has a long history, and there are at least three breakthroughs. The first one is Lyat in 70s and 80s. He used the two-body potential and in the Skarm-Hartree-Fock without a density-dependent term. And Lanskoy and Yamamoto in 1997 proposed that the Skarm-Hartree-Fock with one density-dependent term should be added as the other nuclear Skarm-Hartree-Fock calculations. And recently, Choi and Hiyama et al. Found that the Skarm-Hartree-Fock with two or three density-dependent terms significantly improve the result with the case of the just one density-dependent term. And Skam-Hartree for lambda hypernuclei, the equation looks like this. And I'm sorry, but we ignore the LS first term because it is known to be small for lambda hypernuclei. And this is the lambda potential in nuclear matter. And this part is shows the effective mass term, which comes with the Skam density-dependent force. Okay, therefore, this M star and this U lambda part is given by the chiral EFT. In chiral EFT, the lambda potential is in Skam-Hartree calculations, and the U lambda is given as this one, and rho is the nucleon density, and tau n is contains the rho times kn square. Therefore, this is a nuclear momentum dependent term, and this is a Laplacian term, and density dependent terms, two terms here, 4/3 and 5/3. Therefore, in the case of the zero momentum in uniform matter limit, then we have the density to the first and the 4/3 and 5/3. And these parameters are already known from the chiral potential. And for the 5/3 terms comes with the direct 5/3 term and the nucleon kinetic energy term. This contains the nuclear momentum square. Therefore, density times k square gives you the 5/3 in uniform matter. And the momentum dependence is assumed to be proportional to the nucleon density times the momentum square. And this term is tuned to reproduce Kono's result at low momentum. And the finite range effects, S3 lambda here, is tuned to reproduce the separation energy of lambda in carbon-13 lambda. Since carbon-13 lambda is composed of one lambda particle and carbon-12, which is just even nuclei. Therefore, this is a very good nuclei to be described by Skam-Hartree calculation in the spherical assumption. And since the mass number of carbon-13 is not large, therefore the density derivative should be large in this nuclei. Therefore, we reproduce this carbon-13 lambda binding energy of lambda and fix this A3 lambda. Then we now fix all these terms. Okay. And this one I already showed. Okay. And at least up to around the Fermi momentum at normal density, then the k square dependence seems to be enough to explain the chiral EFT result. And up to 2 rho 0, it is well described by this parameterization. Okay, let me go to the real result. When we compare the result of chiral EFT result without 3-body force chi2 and with 3-body force chi3, then what we have found is that we can roughly reproduce the binding energy of lambda at the heavier hypernuclei well by chi3, but the chi2 overestimates the binding energy of the lambda and heavy hypernuclei because at around rho 0, chi2 gives deeper lambda potential in nuclear matter. Therefore, this difference is around 3-4 MeV, And we overestimate the separation energy or binding energy of lambda by 3-4 MeV here. And then we cannot help this chi2 because momentum dependence or the finite range term cannot modify the binding energy at heavier nuclei. Therefore, chi2 is does not explain the hypernuclear separation energy. And we can now forget about it. With the momentum dependence in chi3, then we can explain the mass dependence of the separation energy of lambda from carbon-13 to lead-208 lambda or something like that. Okay. Therefore, a chi3 with the momentum dependence explains the data. Well, that is the situation. But now we have a question. The chirality and the meson exchange-based potential have different density dependence as this one. This is the Lansky-Yamamoto potential, and the chi3 potential have a very different density dependence, even at lower densities. Then why can both of them explain the binding energy of lambda? That is a question. Therefore, we have made a global analysis using Taylor coefficient around rho 0. J is the depth at rho 0, and L is the derivative, and K is the curvature. And this term is corresponds to the M star, and the other effects are ignored. What we have found is that there are two local minima. One of them corresponds to empirical lambda potential for hypernuclei. The other local minima corresponds to the chi3 repulsive potential at higher densities with a large curvature. And therefore, since there are two local minima in this kind of parameterization, then we can explain with this one as before, and the other new local minima correspond to the chiral FT. And therefore, because there are two local minima, then the density dependence is different, but both of them can explain the data. And we have found it very recently, and I'm not sure this works well for example, relativistic mean field or point coupling relativistic mean field or other framework, but this may give a solution to the hyperon paradox. That is my hope. Okay, let me summarize this talk. I discussed that the lambda potential in nuclear matter from the chiral theory with the three-body force effect is examined via the Hebbian collision data, as well as from the binding energies of lambda in hypernuclei. And with the chi3 momentum, repulsive U lambda forbids lambda to appear in neutron stars, and the hyperon puzzle is solved. And this chiral lambda potential from chiral UFT is explains the first explains the directed flow lambda, and it is very important to measure them at the lower energies such as root S is 3 or 4 JeV, which corresponds to the fair energy, which reaches around up to 5 JeV in colliding energy, or the 3 JeV at high F, which is will be constructed in China. And at these energies, then the directed flow of lambda is well explained by the chi2 as well as by chi3, provided that the momentum dependence is not very strong. And the chi3 mom, chiral EFT potential with three body force with momentum dependence can explain the lambda binding energies. We need to tune the finite tensor, but the chiral 3 without momentum dependence underestimates the binding energy of lambda for finite angular momentum states, but the chi3 mom explains all the binding energies. But the chiral 2 is too attractive and cannot explain the binding energy of lambda. As discussed here, the hyperon puzzle would be accessible via laboratory experiments. And our conclusion is that the stiff lambda potential at high density, having momentum dependence, explains both the directed flow of lambda from heavy collisions and the binding energy of lambda in hypernuclei, and provides that the U lambda, lambda potential is not very repulsive at high momentum. Therefore, this support the solving the hyperon puzzle in neutron stars. And our conjecture is that there may be two types of lambda potential, which explains the binding energy of lambda, Lyons-Koyamamoto type or the chiral FT type. And lambda appears in neutron stars in the former, but lambda does not appear in neutron stars in the latter. Therefore, if we did know that there are two local minima before the observation of two solar mass neutron stars, then we could say that the neutron star chose just this local minima. But since we did not know this second minimum, then the neutron star's hyperon puzzle appears. Of course, there are a lot of things to do, but it's already 70 minutes, therefore let me stop here. Thank you very much for your attention.
Okay. Yeah, thank you. Thank you for the very nice talk. So now we are open for questions and comments. If you have any question, you can raise your hand or you can just turn on your microphone and speak. Xiaofeng, please.
Yes. Hi, Akira-san. Yeah, very nice talk.
Hi, Xiaofeng.
So I'd like to ask. So experimentally, do we have any method or way to directly probe the three-body force? For example, currently here that you are using the direct flow and binding energy. It's kind of like indirect way.
Yes. Therefore, one of the way may be to measure the three-body correlation function. To see, for example, the ALICE members measure the lambda PP correlation function, and if the three-body force is strong, then the three-body force effect may appear in the correlation three-body correlation function. That is a kind of really direct method. But of course, we have to subtract the effect of the two-body force from the three-body correlation function. And I'm not sure we can achieve the precision to extract the three-body force from the three-body correlation function with the precision because the lambda-n interaction uncertainty is still there. And we really need very precise FADEF calculation, including the two-body and three-body interaction. And that is the thing which we should do, but the uncertainty in the lambda n two-body interaction is not very small. Therefore, I'm not sure we can really extract the three-body force directly from the three-body correlation function. And that's one thing. And the direct, you mean experimental direct way. In the case of theory, then the three-body force effect in the binding energy is direct, but you are not satisfied with that answer. And the three-body correlation function is a direct way, but the other one, I'm not sure. And as you know, when we use heavy-ion collisions, almost everything is a kind of indirect. And the people say that the lambda production cross-section, I mean that the formation rate of lambda particle may help us to understand the three-body force effect or something like that. Because lambdas are produced dominantly in the dense region. Therefore, when the lambda potential is so repulsive, then the production rate of lambda may be smaller. But we have not worked in that. But anyway, you can run the code. Now anyway, JAM2 is already open source code, and you can run. But it may take. But anyway.
Thank you. Yeah. I think it's very good. Yeah, the correlation function maybe performed contact in low energy experiment to test the three-body. May I?
Yes.
Have another question?
Of course.
So about the binding energy of the lambda is at the saturation density. So do we also test in some other density region of this binding energy?
You mean that the up to around the saturation density, then we can probe it from the binding energy because we have the density profile of nuclei, and one lambda is inside the nuclei. Therefore, up to around the saturation density, then we can probe the density dependence of this part. But you mean that for different density? You mean above?
Experimentally,
It is still indirect, but for example, in the case of the lighter nuclei, then the dominant part comes from lower density part. And for heavier hypernuclei, then it probes the larger density part. I mean that the around rho zero is probed with the heavier hypernuclei, and the lighter hypernuclei probes mainly the lower density part. That is my understanding. Therefore, the understanding the light to heavy hypernuclei from carbon 12 or 13 lambda to lead 208 lambda, then we can probe the low density to higher densities. That is my understanding, but it is still indirect.
Yeah, maybe my question that in heavy collisions, we may have a different collision energy. We have density change. So the binding energy, I'm not sure whether the binding energy of lambda will also change. That, for example, we have different baryon density. Can this also used to test that density dependence of this binding energies? That's my question.
During the heavy-ion collisions?
Yes. So in heavy-ion collisions, we have different collision energy and produce hypernuclear, for example, hypertriton, different energies.
Yes, in heavy-ion collisions, for example, in the case of the 5JF, which is achievable in CBM, then the highest density may reach 3 rho 0 or something like that. But if the hypernuclei is produced and observed, then the final the observed hypernuclei exists outside of the hot and dense region. Therefore, the binding energy produced from heavy-ion collision should be the same as that produced in the vacuum. No?
Okay.
Therefore,
okay. Yes, thank you. And
okay.
And maybe one note is that recently we have STAR has submitted the flow of hypertriton 3 GeV.
Yes.
Yeah.
Thank you.
Yeah, maybe that it's interesting for you.
Of course.
Okay.
I'm not sure, but it contains more things to do. We have to make a coalescence to form the hypertriton. Oh, hypertriton.
Yeah,
okay.
The direct flow of hypertriton 3 GeV. Yeah,
okay. It may be related to really related to the three body force or density dependence. That's right. But I'm not sure we can distinguish. But you submitted the proposal, means that there should be some theoretical support. Can you hear me?
Yes, I can hear you. Yeah.
Then you should have some theoretical support from someone. Who? Anyway, I have to check. Okay, thank you.
Okay, thank you. That's all my questions. Thank you very much.
Any other questions or comments? Akira, have you used your Chi3 calculation to extract the equation of state of a dense matter?
Oh, yes and no.
In the beginning, you said that that's the puzzle.
Yes. My point is that since there is no hyperon appear in the neutron star matter, it means that the equation of state is the same as nucleonic equation of state. There is no change of the equation of state by hyperons. That is the suggestion. That is the suggestion by this kind of chiral EFT potential. Therefore, I haven't calculated the equation of state, but the answer is the same as that in the without hyperons. That is the answer.
So you mean if we increase the density, we just go from the usual nuclear matter into at a very high density the quark matter without
without going through the hyperon phase.
Okay, without producing the hyperon. But
But
in the conclusion part, you said there are two minimals, and one would suggest the appearance of a hyperon in neutron star matter.
Yes,
right.
Well, with this one, with the curvature of 300 mel, then the hyperon appears in neutron star matter, and we cannot support two solar mass neutron stars.
Oh.
Therefore, this one is already ruled out from neutron stars.
I see.
This one is not ruled out. because the hyperon does not appear and the equation state is not softened. And and this above one, the first local minimum was has been well known, and this is empirical one. Most of the empirical lambda potential shows around this value, and cause the neutron sub hyperon puzzle. But this one does not cause the hyperon puzzle, but the lambda does not appear in neutron star. Therefore, it's less interesting in view of the hypernuclear physics, but the this is a new local minimum.
I see.
Is there a way that for
Yes.
another hypernuclear binding energy that you make a prediction from these two potential models that you will see the difference so that we can differentiate based on the binding energy?
I hope so, but when we seriously compare the binding energy of lambda in hypernuclei, then I'm afraid that the SCAM-Hartree fork is not enough. I mean that, for example, in the SCAM-Hartree fork calculation, on a spherical assumption, then we ignore the residual interaction such as a spin-spin interaction or valence nucleon lambda interaction or something like that. We just ignore the residual interactions. Therefore, I think that there's some kind of more serious calculation such as the more serious estimate of the binding energy using chirality by using the, for example, there are several calculation methods such as hyper unsymmetrized molecular dynamics or other cluster type or few body type structure theory. Therefore, by using such kind of theory, then we can distinguish the two types of local minima. I agree that, and that is the thing which we should do next. That the thing, but I'm not sure my student is interested in this kind of direction or not, and therefore probably I need to search for someone who runs this kind of direction.
Okay,
And that's
thank you.
my guess. Yes. And there are several proposals to measure this hypernuclei, and then we may see the three-body effect. But the this local minimum and this local minimum is somewhat different from the smaller lambda and three-body force, but the density dependence itself is different from the two-body level. Therefore, I think that we may see more clear difference in the lambda lambda binding energy. That's my hope, but I'm not sure. Anyway, more serious calculation based on these two local minimum is, I think, that's a very interesting future work by someone. I'm not sure who can do it.
Right. In recent years, the lambda spin polarization is a very hot topic in the heavy collision community.
Yes.
And
Yes.
now there is, as far as I know, there maybe very few study about the hadronic interaction effect on lambda polarization. But the measurement shows that even down to 3 GeV, the lambda spin polarization is very sizable. So maybe I don't know, maybe the lambda spin polarization can be a way to detect the lambda potential in nuclear matter. Suppose we can measure the suppose we can measure lambda polarization precisely at a very low energy. Because the angular momentum is very closely related to the V1 slope. So maybe
I do not have the answer, and I haven't considered it before. Therefore, I don't have the answer. But you see, but you said that the polarization is closely related. Angular momentum is related to V1. That's right. And that's right.
And it's also induced the lambda spin polarization. So I wonder whether there is a connection between lambda spin polarization measurement and the lambda potential in nuclear matter.
I think that's a very interesting question. While I do not have the answer. Thank you very much for your comment.
Okay, thank you.
But
okay, Kaijia, you have a question?
Yes, thank you. Thank you, Professor. You mentioned the V1 of proton, right? And
yes.
it seems that you can explain the slope of V1 of proton without any phase transition, right? Because some earlier studies suggest that the change of the slope of V1 is due to the occurrence of a first order QCD phase transition.
Yes, I also wrote the paper on that line. Yes, in the case of the free fluid dynamics and the first order, second order, I'm not sure. Anyway, these are star data, and we at low energies the result without phase transition explained, but I forgot which line is which. But anyway, black dashed line explains the data this one, but it does not explain the data at the high energies. Red line it does not explain the data at low energies, but at around the 10J, it explains the data. In our result, then that is with Xiaofeng? No, not yet. Anyway, in the case of ours, then this one explain that the standard jam hadronic transport explains the data at low energies, but at higher energy, at around the transition energy, then we need a very attractive one which simulates the phase transition. That was the situation, and therefore from this one we claim that the early sign change of the Boolean slope of proton shows the softening of the equation of state from here to here, but by changing the equation of state as a function of the colliding energy is not satisfactory, because the equation of state as a function of density and momentum or something like that need to be the need to be the same and independent of the colliding energy. And all the previous works result says that we need to modify the equation of state as a function of the colliding energy. And in our case, what happened is that at lower energies, the density becomes high and the V1 becomes large. But in the later stage, then we have the tilted matter, and which emit the protons in the negative V1 direction. Therefore, it becomes smaller in the expansion stage. and becomes goes to the final result at around 10 GeV, and it becomes negative. And there's a balance of the initial repulsion and the later negative contribution from the tilted matter, and this difference cancellation determines the final V1 result. That is our finding. And in order to have this tilted hot matter formation, then the interaction should be shown even at high momentum. Therefore, we needed the vector type potential vector implementation of the potential in hadronic transport model calculation. That is our finding in this Akira Ohnishi paper. And for example, in the case of the 3FT, the initial part is missing because they prepare the initial condition from around after the collision. Then I'm afraid that in 3FT, then the initial repulsion may not exist. And in the case of the hadron string dynamics or partner hadron string dynamics, I'm afraid that they use the momentum independent interaction in the equation state. I'm not sure. Do you have someone who is a cause of this? I'm not sure. And the momentum dependence is also important, and therefore they also fail to.
So you mean the measured V1 can be explained solely due to the hadronic interactions, not through the first order crystallization?
Yes. And softening is not necessary, but we do not deny the possibility of softening yet. For example, the softening. We draw our curve here. We say that we claim that we explain the data well, but when we see this part closely, then we do not completely understand the data, and the V1 becomes smaller, goes to 0, but our result says that it is still decreasing. Therefore, from around up to around 11 GeV or something like that, then we explain the data. But at 20 to 30 GeV, then we do not reproduce the data. And this is the region where really the QGP may be formed. This may be the energy of onset of the confinement. Therefore, probably, and anyway, softening is not denied, not ruled out yet, but there is at least one way to explain the V1 slope and colliding energy dependence of the V1 slope. That's our message. And that message is that up to around 11 GeV or something like that, hadronic matter may be dominant. That is my guess.
Okay, thank you. Thank you for your nice explanation. Thank you.
Yes, and maybe this part may be more interested by your group, I'm afraid. Anyway, main part is yes.
So any other
Yes.
question or comments? Yeah, I think we really already have a lot of discussion. So I think we stop here, and let's thank Professor Ohnishi again for the very interesting talk. Yeah, thank you very much.
Thank you for your discussion. And yes, I need to consider the hypertrophy directed flow. I'm not sure. And other.
And
Okay, anyway.
maybe start observe not only hypertraction but also helium 4. Maybe the experimentalist can.
Yes, hyperhydrogen 4.
Oh, okay.
Right.
Yes.
So in that case, do you need also 4-body force or to make the calculation?
Do you have reliable 4-body force effects?
I don't know. I don't know.
Yeah, this is actually very interesting because in experiment, we can, for the correlation function for the fundamental study, it's easy to extend it to a 3-body. Then we just follow the same cumulus method. It can be, so in principle, it can be extended to the 4 or 5 or whatever, but this is just up to you. First, from the theoretical standpoint, you need to give us a motivation. Then we, because the general cumulant, the framework is already there. It's proposed by the Kubo, right? Kubo-san. And then now Laura's group, actually we are also member of Alice. We're closely, together working with Laura. Actually, very recently, we just dispatched one new PhD student, sent him to TUM and working with in this direction. So due to the time limitation, I didn't ask, but since Shigua mentioned this, I would also like to ask about this. So far it's not under your consideration.
Not yet.
Okay.
In addition to the constructing the 4-body force is at present out of the scope of chiral FT, I guess. That's one thing, and the other thing is that the 4-body wave function is not easy to measure to calculate. Even with the 3-body force, then we need the Faddeev equation, which in the continuum energy state, and for any energy and any continuous energy, and it's not easy. And only a few groups in the world can calculate such kind of Faddeev calculation. That's one thing. And in the case of the 4-body wave function, then there is only 1 or 2 group can calculate the bound states. And for continuum states, then for bound states, then many groups can calculate, but for continuums, then the 4-body calculation is not easy. Therefore, only a few groups can calculate, and it takes a lot of time for the calculation itself. Therefore, I don't know. And the recent Alice data says that the real Faddeev calculation is necessary to explain the 3-body correlation function. It means that we really need the 4-body or 3-body calculations. And
so far for your lattice QCD calculation for the 3-body correlation function, you don't have any solid result yet.
3-body?
Yes.
3-body correlation function? Oh, I did not calculate the 3-body correlation function yet.
Okay.
I'm sorry, but at present only the PISA group calculates the three-body correlation function. And I just made some kind of the boron expansion and the effect of the three-body force in a perturbative way, just like that. And that's the situation. And I haven't calculated the three-body wave function yet.
Okay, no problem. Thank you.
Yeah. Okay. Thank you, Akira. Thank you
very
very much for the nice
your
talk.
invitation.
Hopefully we could, I think this year, hopefully we could meet in person somewhere in some meeting.
Yes, let's see in person somewhere.
Right. Okay. Thank you. Okay.
Thank you very much.
Okay. Bye.
Recording stopped.